speaker, Sattik Bhaumik. I hope I'm pronouncing your name correctly. Sattik, are you there?
Yes, sir, and you have pronounced my name very correctly.
Okay, great. So Sattik will be talking about using astronomy archival data at high school level. So you have 15 minutes, and then leave 5 minutes for question and answer. Welcome, Sattik.
Yeah. Hello, everyone. I'm Sattik Bhaumik, a 12th grade student at Don Bosco School, Siliguri in India. The topic of my presentation is using astronomy archival data at high school level. Before we dive further in, I would like to give a brief info about my activities in astronomy. I'm a member of Skywatchers Association of North Bengal, abbreviated as SWAN in India. We do a lot many public astronomy outreach events. I've also been a part of SWAN Asteroid Hunters team. We took part in the International Asteroid Search Campaign last year, and we found about 5 potential asteroid candidates, out of which one of them got a preliminary status and has been temporarily named as 2020 JK11. I've also been a part of citizen science missions such as Stardust, IASC, supervised variable stars through the Zooniverse portal. Currently, I'm conducting my research under Research Discovery Program on determining habitability of exoplanets using Python. This research is mentored by Dr. Gitanjali Sethi, who is an associate professor at St. Stephen's College at Delhi University. Now, what is archival data in astronomy? Some people even prefer to tell it as raw data. To define archival data, it is a form of data that is collected prior to the beginning of any research study and is made publicly available for everyone. Now, how can we access this particular archival data? Well, there are databases such as NASA's Extragalactic Database, Exoplanet Archive, TUMAS, SIMBAD, etc. And there are even catalogs where the research findings and new discoveries are cataloged, and you can even access their original raw data for free. Such catalogs such as exoplanets.eu, .org, NEXI, PHL are there. Now that we know what is archival data, what can high school students do with this form of data? Firstly, they can take part in various citizen science programs like Stardust at the Rate of Home by NASA, asteroid search collaborations conducted by IASC throughout the world, and various planet hunting events such as Planet Hunters tests through Zooniverse. They can even take part in workshops such as Sagan Exoplanet Summer Virtual Workshop conducted by NASA, IPAC, and Caltech. Or the students can conduct their own original research independently from summer schools, workshops, and actually get published. The topic of my research is determining habitability of Kepler 504b, Kepler 315b, and Kepler 315c using Python. Now that we're determining the habitability of exoplanets, what are they? Well, to define exoplanets, these are planetary objects that are not a part of our solar system and they revolve around other stars. Now, what are the methods with the help of which we can actually discover that these exoplanets exist or not? Various methods have been developed, and all of these methods require their own specific way of collection of data for analysis. The most popular among them is the transit photometry. So what happens is we record the brightness of the star over time, and we look for what we call as periodic dips in the brightness. So as you can see in the animation, as the planet passes in front of the star in our line of sight, there is a dip in the brightness. So we record these dips, we look whether they are periodic or not. If they are periodic, yes, there is an exoplanet. Now, here is a comparison slide. With the help of transit photometry data, we can estimate how big the planet is. A bigger planet will give you a bigger dip in the transit or the flux. A smaller planet will give you a smaller transit. Now, here's a problem with transit photometry data. What we can calculate the orbital radius, the planet radius, temperature as well. But if we calculate the mass, it involves a high degree of uncertainty. To resolve that, there is another method called the radial velocity method. In this method, we record the absorption spectrum of the star. So as you can see here, the planet and the star actually revolve around each other at a common center of mass. We even define it as a wobbling star. So we record the absorption spectrum, as you can see here, and using this through Doppler effect, we create a plot of the velocity of the planet against time. Now using this plot, we need only one value, which we call as Vmax or velocity semi-amplitude. There is a formula where we just need to plug in this Vmax value and the mass of the star, and we'll get the mass of the planet with utmost precision compared to transit photometry. There are other lesser known methods as well, such as this one is the direct imaging. It's been taken by the Keck telescope. It's an infrared image of the star HR 8799. As you can see from this image, there are 4 planets revolving around this star. The only disadvantage to direct imaging is it consumes a lot of time for detecting exoplanets and a lot of resources. There are other methods as well, such as astrometry, gravitational microlensing. But the disadvantage we have with those methods is because of the technological constraints and the telescope capabilities constraint, due to which we cannot fully access or fully use these methods to the 100%. Now that we know the methods of detecting exoplanets, I'll move on with tools. Well, for my research, I have used the transit photometry data of the star. And along with that, I'm using Python. What is Python? It's a general purpose programming language. It's lightweight, very flexible, and can easily perform complex mathematical and astronomical calculations. As you can see, these 2 images, this is the code I made after learning Python and going through the light curve module. Now, what is the use of this code? Well, we will input the star name here, enter Kepler star name. So after we have inputted the star name, it will give us certain plots. For example, this one of the star Kepler 54b, this is the stellar data. So using code, I'm able to extract the plot. This is the flux or brightness versus time. Now we will apply a method called BLS periodogram or Bob's least squares periodogram. What does that do? For a certain period, say out here, as you can see, it's 20 days. It will convert those flux dips, those transit dips, as we saw in the animation of transit photometry, into power. And then over that period, it will look for the maximum power. So from the plot, as you can see, there is a very significant big power here. So it indicates that, yes, there is a planet transiting the star, and it will also give us the corresponding period. And that is about 9.55 days. Now, using this period to just ensure or validate that, yes, there is a planet, we plot a folded light curve using that period. Now, there are 2 purposes that this plot serves. Firstly, we are confirmed that, yes, there is a planet. As you can see, there is a light curve out here. There's a dip in the transit. And using this planet, we extract a value called F minimum or flux minimum. What we do is we take this flux minimum value as here 0.9979, and we use this to calculate the planet radius, then temperature. Similarly, for the star Kepler 315, the first planet we get, Kepler 315b, has a period of approximately 96 days. Now, here's a catch. For the star Kepler 315, there are 2 planets. So now that we have already found out the first planet, we plot the folded light curve as well, and we note down the F minimum value. We are going to do a process which we call as masking. So what we are going to do is, as you can see here, the red dots. So these are the red data points that we are hiding from the original stellar data. So now for finding the next planet, what we are going to do is that we have hidden the data, so it won't be used for further plotting or further calculations. So after hiding or masking, we apply the BLS power method again, and we see that over a period of 300 days, there is a significant maximum power of transit out here. So this gives us an indication that, yes, there is a second planet called Kepler 315c with a period of approximately 265.5 days. To ensure ourselves again, we plot the folded light curve, and yes, we see you can apply the bind flux in any plot. This has been given here to just ensure, because some plots might not seem that good because the flux dips might not be that significant. For that, we have used the bind flux as well. You can apply those in the previous plots also. So now for the 3 planets, we have the orbital period and the F minimum value. Using these 3 values of the 3 planets, we are going to calculate the planetary parameters. What? We already have the orbital radius. We get the orbital radius, then we calculate the radius in terms of Earth and Jupiter. Then we calculate the temperature. Note one thing, we have calculated this particular parameters of the planet using Python code. Now, since I have used transit photometry, I have not calculated the mass. What I have done instead is I have imported the mass value from the NASA's Kepler data archive for these 3 particular planets. So after I get the mass value as well, I can calculate the density and eventually the escape velocity. Now, remember, the original goal of our topic of my research was determining the habitability. How will determine the habitability? Using an index called ESI, or Earth Similarity Index. ESI can be defined as a ratio of comparison where we compare the exoplanet to our planet Earth. Here's the formula. ESI of any parameter X, say radius or density of any parameter, is calculated using this formula. And over here, W of X is the weight exponent of that parameter for Earth. If we would have used Mars as the reference, it would have been Mars Similarity Index. The weight exponents would have been different. Now, here's a snippet of my Python code that I've used for my ESI calculations. As you can see, we have already inputted the Earth data, its density, escape velocity, temperature, and also the weight exponents. You can get the weight exponents value from Planetary Habitability Laboratory website or the MAST portal or the NASA's Kepler Data Archive as well. Then I've calculated the ESI for 4 parameters: radius, density, escape velocity, and temperature. After calculating the ESI, I further calculate the interior ESI using the ESI of radius and ESI of density, and then the surface ESI using the ESI of escape velocity and the ESI of temperature. Then we calculate what we call as the global ESI or the final ESI. This is the ESI value that will actually tell us whether the planet is habitable or not. Now, ESI, since it's a ratio of comparison, the values start from 0 to 1, where Earth has been given the value of 1 since we are taking it as the reference system. So after calculating, this is our ESI result. 2 planets, that is Kepler 504b and Kepler 315c, they have a habitability of around 70%, like 71.2%, 69%. So they are partially habitable. And Kepler 315b is not habitable at all because it has only an ESI percentage of only 36%, 35.68. Astronomers want a value above 80%, preferably better even if we get a value above 85%, because then we are 100% sure that yes, this planet is habitable. Now, let's say that the students, they don't have the time to learn Python and make their own code. What they can do is they can use a software called TopCat Astronomy software, where they just need to download the transit photometry data and the radial velocity data from the MAST portal or the data archive databases. And using that, they can calculate the orbital period and the F minimum value using the folded light curve, and from radial velocity, the Vmax value. Then they have the values, they can eventually calculate the ESI. There is even a third option. Let's say the student does not have the, he or she does not want to do the data collection and the data analysis. He or she is only concerned with calculating ESI values for a given range of exoplanets. So what they can do is they can go to NASA's exoplanet archive and they can use what is there as the online plotting tool. For a particular candidate, as here it is the folded light curve of Kepler 427b, they can directly get this plotted curve, folded light curve. They can download this table. They can download the data of this plotted light curve. And from there, they can get their F minimum value and eventually calculate the ESI they need. Personally, as a student, I did not know Python earlier. So yes, learning Python was a bit challenging initially, but learning those light curve AstroPy modules it was very interesting. It's how it is interesting. It's like those simple lines of code can actually analyze huge amounts of data for you and give you the desired values. And earlier, I used to think of astronomy as a field where like astronomers took the telescope, they went in a dark sky place, they just watched the night sky, studied the stars. That's what I thought. But after this research, I got an exposure to how the actual field of astronomy actually looks like. It's much more than just watching the night sky. I would like to thank Research Discovery, which provided me the platform to do the research on exoplanets. I would also like to thank my mentor, Dr. Gitanjali Sethi, without whom none of this would have happened. And lastly, I would like to thank the Global Hands-on Universe GHOU team for allowing me to share my experience as a student researcher with others on an international platform. The background images were sourced from NASA, JPL, and Google Images under the Creative Commons license. And the code in my Python, it has been used from sources of Lightcurve, Matplotlib, and AstroPy module. Thank you everyone for listening. If you have any questions, feel free to ask them. And you can even contact me on my email, Instagram, and Twitter. Their IDs are given here. And yep, thank you everyone.
Yeah, thank you, Sattik, for this wonderful presentation. There are actually few questions in the chat. One of them is it possible to find the Python source codes in GitHub repository?
Yes, like if you visit the Lightcurve website as well, you can get like the source code in Google Colab, Jupyter, GitHub. It is available.
This source code is available there, right?
Yes, you can get the source code, and like the code which I have made, I will be uploading that in my GitHub repository as well. I have not uploaded it yet. I will upload.
Okay, thank you. From the same person, Francisco, he says that I see Lightcurve Python library is open source, but I don't know if your code is. Is your code open source?
Like I have used the Lightcurve module. I have not yet, like I told, I have not yet uploaded the code. I will upload it and it will be open source for everybody.
Open source. Okay. Okay, thank you. I have a small question, like how many in your group are working in this? So have you tried this with high school students in your group, or so how?
No, sir. Like it is my first time through research discovery platform. There are organization in which high school students can do research along with professionals on the field. So it was my first time high school research.
So are you planning like to?
Yes, further on. Yes, I am
students and so on. That's yes, great.
Sir. Yes, sir.
But it looks that people, they need to know a little of Python.
Yes.
Right.
Yeah. Even if they don't know Python, it's not a problem. They can use Topcat astronomy software. They can use even the online plotting tool.
Yeah, there is a question in the Q&A section by Terina. Hello, Terina. So it says, great work, Sattik. Have you thought of developing easy to follow activities for students on how to conduct research using raw data? That could be quite useful. You can also create an activity that could be published in our International Astronomical Union AstroEdu repository. Well, Terina, you could contact him and then he might actually help you on doing that, because you are saying that you'll be developing such thing, right? Right, Sattik?
Yes, sir.
Okay. So please get in touch with Terina, and maybe next time we need to hear from you some outreach to high school students using your work, actually.
Yes.
There's another question from Francisco. How do you know the planet mass?
Okay, so like the candidates which I have used, which I have taken in, those candidates mass were already calculated and they are available in the Kepler data archive provided by NASA. So I got the mass values from there.
Okay. Well, Sattik, I don't have any other questions. It's really impressive what you are doing. I wish you the best, actually, and what you are doing is great. And also, I liked your way of presenting and respecting the time. This is also very nice, very nice work.
Thank you.
Congratulations, Sattik.